project is the infrared laser gas purge. So during this project, I worked on the DXS EJX1 tile. You can see a CAD model of that in the top middle. So a tile stands for Table Integrated Laser Enclosure, and these provide a path for laser beams to follow. So tiles are open to the atmosphere, and this means that atmospheric elements like oxygen and water can accumulate in the inside of these tiles, and these absorb the energy of the laser beam, producing undesirable results. So the solution for this is to purge the tile with clean, dry air to remove all of these atmospheric elements. But the catch here is that if the flow of the clean, dry air is turbulent, that's also going to create an unwanted interaction with the laser beams, producing more undesirable results. So the purge has to be laminar at all times. So the objectives for this project are obviously to purge out all the atmospheric elements from the inside of the EJX1 tile, create a laminar flow, and I need to determine the parameters of the purge, such as the flow velocity and the size of the holes on the walls through which the purge is happening. And all of this can be generalized for application onto other tiles. So the procedure, the first thing I did was I looked at the CAD model of the tile created by LCLS engineer, and I stripped it down for ease of 3D printing. So basically I removed all the screws, I gutted the insides of all the optomechanics, because my project does not deal with the function of optomechanics, but rather the outer surfaces of optomechanics, because this is fluid dynamics. So yeah, I gutted the insides of the optomechanics, and then after that I decided a scale factor on which to 3D print the tile. So the way we did that was we took a bunch of optomechanics, 3D printed it in like 1/2, 1/3, 1/4. In the end, we decided 1/3 was the best size, so we decided to 3D print it in a 1/3 scale factor. So due to size constraints with our 3D printer, I had to 3D print the tile in 4 pieces. So then after that, I had to design and 3D print 2 tile walls with holes for the purge, and then I also had to design, 3D print, and test 3 different nozzles. And onto the purge, I had to fill the tile with smoke and visualize how the smoke escaped from the tile after I turned on the fan. And if the flow was laminar, which is what I'm looking for, then I could use Reynolds number to scale up the parameters of the flow for application onto an actual tile. So the materials I used. So I had to 3D print 2 tile walls with 8 holes each. So these are the 2 tile walls. And I printed 1 tile wall with 1.55-inch diameter holes and the other with 0.33-inch diameter holes. So 0.33 inch was an arbitrary number given by my mentor, and 1.55-inch diameter, we got that from the diameter of the anemometer fan right here. So then I had to 3D print 3 nozzles, one with a 0.33-inch diameter, one with 0.8-inch diameter, and one with 1.55-inch diameter, and test these with the fan anemometer. Initially, I only wanted to print 1 nozzle, which was a 0.33-inch diameter nozzle. And when we tested that with the fan anemometer, like I connected the fan and blow air to it and everything, we were getting unreliable results on the anemometer. Like we were getting values of 0, even though I could like clearly feel air coming out on the other side of the nozzle. So my mentor said this was likely due to friction on the inside of the nozzle. So the fan was really struggling to push air through the nozzle. So for the time being, I decided that the 0.33-inch nozzle was not valid for use. So then I made 2 larger nozzles, the 0.8-inch and the 0.55-inch nozzle. So then I also got a square USB fan with 3 speeds. That was the first fan I got, but I felt that was too weak. So I ordered a more powerful round battery-powered fan. And I designed a casing for both these fans. This is the round fan casing, that's the square fan casing, and these connect to the anemometer connects to the nozzle. So yeah, I also have the fan anemometer right here. And then I have a polycarbonate viewing window to put on top of the wall so that we can like view what's going on from above. And that's the handheld smoke machine that I used. So how the purge was conducted. I first put the fan into the casing, and then I connected that to the anemometer, and I connected the nozzle to that. And all of this together, it becomes the duct. So then I plugged 6 out of 8 holes in the walls of the tile. So 6 out of 8 holes, like I plugged these 2 holes, and I try to leave 2 holes on opposing sides open because we want the purge to take place over the longest cross-section distance. So to one of the open holes, I connected the duct with the fan and anemometer, and to the other hole, I connected the smoke machine. So then I ran the smoke machine for 30 seconds for each time, and then I removed it, and as soon as I removed it, I turned on the fan and measured the amount of time it took for all of the smoke to be removed from the tile, but I also tried to visualize what the flow was looking like. So these were the 3 tests photos. So basically these were the results. For the first test, I used a round fan with the medium speed setting and the 0.8-inch diameter nozzle. It took 43 seconds for all smoke to be removed from the tile, and the anemometer reading was 2.26 meters per second, and this was a turbulent flow. For the second test, I used a square fan with the high speed setting, a 1.55-inch diameter nozzle, and this time it took 64 seconds for all smoke to be removed from the tile, and the anemometer reading was 1.43 meters per second, and this was also a turbulent flow. So for the third test, I used the round fan, high speed setting, 0.33-inch anemometer diameter nozzle, and this time I got an invalid reading of 0 meters per second on the anemometer and 164 seconds for all the smoke to be removed, and this was also a turbulent flow. So how do I know whether a flow is laminar or turbulent? So a laminar flow looks like this. These are layers of fluid. This is the optomechanic. You can see the layers of fluid are like very well defined here. And in this case, the fluid is approaching the optomechanic as laminar, but it's exiting the optomechanic as turbulent, as you can see from the disintegration of layers here. And this is what I'm seeing here. Like the fluid is approaching the optomechanic already as a turbulent flow, and it's exiting as a turbulent flow. Because as you can see, there's like no layers visible here. And on to Reynolds number. If any of these 3 flows were laminar, I could have used Reynolds number to scale it up. So Reynolds number is RE equals to L over K. V is fluid velocity, L is characteristic length. So for this project, characteristic length is the pipe diameter, like that would be like the diameter of the pipe, and K is kinematic viscosity, which is how much of fluid resists flowing. So Reynolds number is a dimensionless quantity that tells us whether a flow is laminar, turbulent, or transitional. So if I saw that a flow was laminar, I have the values for all 3 of those, and I would just calculate Reynolds number. And then I want to maintain that same Reynolds number when we scale it up. So then when we scale it up, like keep in mind that this is all a 1/3 scale model of the actual thing. So the characteristic length would be tripled, and to maintain the same Reynolds number, the fluid velocity would have to come down by like 1/3. So that's how I would apply it. But unfortunately, none of these were laminar flows, and I would say they all kind of failed basically. So yeah, they all failed. And the first thing I noticed was that the holes in the walls, like when measured from the base of the tile, I felt like they were like kind of high up compared to the height of most of the optomechanics. So this was one mistake that I made, but I could easily fix it by printing more walls with like holes that are lower, so that the flow goes and directly intercepts the optomechanics rather than just flowing over it. And the other solution I thought of was working with a smaller nozzle, because I feel that a smaller nozzle is likelier to create a more laminar flow, because it's like very streamlined, like very finer. It's not like spraying fluid all over the place, which happens as you increase the diameter of the nozzle. But that brings me to the problem I had with this nozzle. So like at the very beginning, I said that this nozzle was invalid because we were getting invalid readings from the anemometer, and that's evident from test 3, because as soon as I used the 0.33-inch diameter nozzle, it read 0 meters per second on the anemometer. So even if that one was a laminar flow, I couldn't use it because I can't do anything with a 0 meters per second anemometer reading. So how would I fix this? Well, then it would become a material science type of experiment. Like then we would like coat the inside of the nozzle with like acetone or oil, or maybe even polish it to like reduce the friction between the nozzle and the clean dry air. And hopefully then we could get some valid anemometer readings and like work with this, and maybe we could even like reduce the size of the nozzle, because the finer it is, the better. And yeah, I guess that's all I have. I'd like to thank my mentors for the guidance. Elon Gallagher, who's my mentor's colleague, for showing me how to do e-print. Joshua Tsui Tang for rehearsing my presentation. And the United States Department of Energy for funding this internship experience. Thank you very much.
We're a little behind, but if anyone has a quick question.
I just have to say that research is not a straight line, right? So neither is laminar flow, but I feel like you learned a lot, even though there was some that didn't turn out exactly the way you wanted it in the end. But did you know how to do the laser printing before you came?
No, that was the big thing I learned, like how to 3D print it.
that's huge. Did you know how to use the other instrumentation that you had, or be able to use the CAD model and reduce it or change the scale or any of those kinds of things?
No, yeah, that's all stuff I learned.
Yeah.
It's-
Yeah, and the importance of why this has to happen in this environment of the laser gas purge and how the accelerator. I mean, I could just go on and on. So I just think I wouldn't call it failing. I would call it learning from what you did, and you already have ideas of what you could do, what could be done next. So great job.
Thank you.